Hello, 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 hello. Here's a microphone. All right, so, well, 2 days of intense talks. I'm going to finish with something a little bit solid on code. So sorry for the advanced tag on the talk, and that was just to say to you that I won't have time to go through what a few of the functions I'm showing are doing. So I'm just giving that as an assumption that you know a few of those things. That's why I put it in advanced mode, but I didn't want to seem presumption, so something like that. So shall we add a P? Just a couple of words about me. Software engineer. I work for Droid Tech. Is a fintech doing automation, like a machine automation of financial law, which is a very interesting field. Of course, we're hiring. Everybody is. So come talk to me if you want to know more about what we do. I'm also organizing papers with love, so a little plug for that. If you read papers, scientific paper, computer science papers, and you want to share that love with us, dig that up and on meetup.com, Papers We Love London, and you'll find an email, send me an email, I'll get you a slot for a month. I'm also author of The Closure Pills on YouTube. Now they are in standby because I'm also known as Mr. is finishing a book or about to finish a book. So when are you going to finish the book is the next question. So it's very close. Last chapter, I think it is going to be content complete by Christmas. I allocated my holidays for that, and that should be it. Then there will be a few passes of editorial review. It's a lot of pages. It was a lot of work, 1,500 hours of work on the train at night because I have a full-time job as well. So that's why it took so long. But back to the talk. So context, we're around 2007, 2008, and we are talking about the fact that CPU speed is stopping up at some amount of megahertz. It's not going beyond that. But cores are still increasing in the CPU, so we have this amount of cores that are coming up. And parallelism seems more appealing, and that's why we think about how more manageable is to model concurrency with functional languages instead of object-oriented languages where state is involved and is more difficult to think about. And that's why we also had a return of functional languages. And Clojure is about that age. And Clojure itself has a very good support. I mean, parallelism is baked in, concurrency is a very serious feature of Clojure, and it is actually a selling point. And it comes with some rich set of APIs. You might recognize some of them: PMAP, p-values, pcos. Those are the lazy, sequential, and chunked parallel processing API. And then we have reducers since 2012, I guess, or something like that. And fold, along with that is applying a slightly different model of concurrency called fork join. Is coming from Java. We are just using what the good fellas at Sun Microsystem and then Oracle gave us. And you can still customize and do your own future agents and stuff like that. And it's not exactly Clojure, but it's very close to it. CoreSync also contains concurrency constructs, parallel construct like pipelines that can apply transducers in parallel. All nice stuff, but I thought they're kind of low level, and the reason is that when you try to use, they're not exactly easy, and even more when you try to use them correctly. And there are a few things that are not integrating perfectly with the rest of the standard library, and one of them is what are we doing with stateful transducers? We cannot, at the moment, we can't use them in parallel. We cannot use them with fold, but why we shouldn't, or what do we need to do? And also things like PMAP, as they have a dependency on the chunk size, meaning that the collection you are iterating over in parallel is deciding how many threads are going to be running in parallel. It's usually 32, but if you, sometimes you need to create your own lazy chunked sequence, you might give a different chunk size. And if your chunk size is 8,000, well, you're going to have 8,000 threads running at once, and it might not be, well, definitely it will collapse the JVM straight away. So can we think it differently? Maybe. What I'm thinking is, can we make it, we have low-level APIs, can we make it task-oriented? So when I want to apply parallelism, I'm not thinking I want to use PMAP. I have a task. I have a big collection. Maybe I have some computation to do. And I have a task in mind. Can we model using tasks instead and make it predictable, more in the sense that maybe it's not dependent on the chunk size that I might be aware or not aware of. Easy to use, that would be nice, of course. And it's very similar to what the standard library is offering in terms of tasks when you think about frequencies, distinct, I don't know, other very popular functions that we're using every day to do collection processing. So very similar to that. So I thought, can we model it like that? Yeah. Challenge accepted. I started working on some ideas. The principles I want to follow are modeling the API of this, or modeling parallelism on top of what we have in the standard library when possible. If it's a drop-in replacement, I can take the function that was sequential and drop in my parallel version. That's, if possible, very good. We'll see at the end if it's possible or not. Transducer support, just because they are pervasive when you do collection processing, so that will be an easy, a nice thing to have. And new function on top if I need to, well documented, benchmarked and tested, and all those nice stuff. So I worked on this current lineup of functions that I made parallel, and I'm trying them out in projects. Hopefully somebody else is using the library. Does anybody know about the library parallel? And okay, fantastic. That's why I'm presenting it. So, so I have a parallelet, a parallel slurp to slurping files in parallel. Do to, count is transducer aware. Frequencies, group by, update vals, which is a new thing, but is updating values in a map in parallel. Sorting in parallel, that might be useful. External sort, if you have large files, you can use this. It's all documented. And I also started to think about the transducer part of it. So I have a parallel fold. We already have a folding core in the reducers namespace. This fold is transducer aware in the sense that it allows stateful transducers in a way that we are going to see in a second. Then on top of that, I modeled other functions like transduce, processing a folder, which is giving me all the files in a folder. I will process them in parallel. Minimum, maximum, distinct, and a few things like for arrays, parallel array map and parallel reverse array map, and interleave map and identity. A few transducers that are useful in this case, and I added them as well. Interesting, the pmap as a transducer is like a pmap operation that you can use as a transducer as part of a transducer chain. So quick REPL, because it's probably the best thing is to start to see a few of those. How we are doing with the font size? Good? Can you see it? No? Well, I hope you can see. I can make it slightly bigger, but then, well, the next example we'll see. So I have here a few quick examples. Let's take a few RSS feeds. They're still around. And I'm doing a concatenation of the news in them. We are not seeing the news, but trust me, there are news. And I'm taking a few of them. So the idea is that I have a let. Let me close this one so you can see below. So I have a let, a block that is executing those sequentially, because that's how the let works. So can we add a P and see what happens? All right, we're doing 1/3 of the time. So my time measurement here, I'm not using a benchmarking library. I should. but these are usually longer operations, so we can see that it's speeding up things. So we are not measuring, we are just measuring essentially the relation between the two, but I'm not precise. But you can see that it's speeding up. So what's happening is taking those feeds, executing them in parallel, and then concatenating them at the end. So slurping. I have this large book, War and Peace. I can do it normal slurp or parallel slurp. Yeah, there's a time advantage. It's still very fast, so 40 milliseconds versus 80 or 73 milliseconds. So you don't see a lot of difference, but it's kind of a half of it. And the larger is the file, the more you can get. And I also started to add things into standard library functions like that are not there. For example, what if I pass a function to slurp that is doing some processing while it's loading the file? And with that in mind, I can do things like not just reading from a text file, but also reading from an archive, like a jar file, and slurping from a jar file and get the content out. And it's doing it in parallel again. Counting. Counting is another operation that is difficult to beat in general because most of the closure collections are constant time counting, so there's nothing really to beat there. They're just returning in constant time. But when counting is applied to a collection where you're doing transformations, you don't know the count, I have the time. And you can see here I'm counting in multiple different ways, counting the words in War and Peace. I'm also, to be fair, I'm using transducers, which is a better way, but Into is also using transducers, so I'm not sure there is a lot of difference there. And then going for parallel count, so let's have a look. Also keep an eye at the numbers down there while I'm doing this. And you can see that we are progressively going faster and faster. So from the 2 seconds down to 300 milliseconds. Frequencies, and then we'll stop here because I have many more, but I want to show you another more consistent demo later with much larger stuff. Slurping War and Peace again, and we are doing what? Frequencies of words, another classic. So we are seeing many different ways of doing that. We have classic frequencies of processive lowercase of words, and then I'm doing my parallel frequencies, mapping over the words, and then I'm taking map as a transducers and bringing it out, which is a new feature of frequencies, so I can pass a chain of transducers, and when it's out, it's even faster usually. Yes, it is. 25 milliseconds. So we are still going down there as well. So as I said, I have a thing I want to show you, so I'm not going to show you all the functions I have, but those are documented on the project, so if you want to have a look. So let me make it bigger, and I'll go back here. So I was saying, let's have a look at something more challenging. So I took the LastFM data set, like a kind of an oldish version, is about 10 years old. But it's still useful, I think. So it contains thousands of users, activities on the LastFM website, and LastFM is collecting all your plays. Every time you play a song, it's collecting what song are you playing, and giving you recommendations and stuff like that. And this data set is quite large, as you can see. There are actually 2 of them. It's 1.5 gigs of 360,000 users. It's a 1.7 million lines tab separated file. And another one which is even larger with all the detailed plays. The other one is aggregating by band or artist name. And the second one, which is larger, is every single song you played. And it's got also some user demographics. So I thought, let's try to do something that is more realistic and apply those parallel functions to this. But I want to show you a first and after sort of thing. So I'm trying to do my best and using all the best practices I know to load and process such large files in Clojure without using parallelism first and then using parallelism behind my library after. So what you want to do is you want to be lazy. You can't load the content, all the lines in the files, and split them into vectors to do processing at once, because it will, unless you give it, I don't know, 16 gigs of RAM, it will probably go out of memory. So of course you can throw as much memory as you want, but I'm trying to stay. If I can stay lazy, I'll be lazy, meaning I read the file, I move through the file, and I'm processing the file as I go, and I'm forgetting about the rest of the file, and I'm aggregating data and doing calculations. I'm using transients, again, to be as fast as I can. I'm using transducers instead of composing sequential processing. And in general, I'm being careful with eager functions like frequency, sort. Those kind of functions, if you give it all the data, they will load everything in memory and do what they need to do, but they will give you out of memory most of the time with such large files. So more demo, as we're spending a little more time in this code instead. Okay, LastFM. See if I can make a little bit more room. No numbers. And no numbers. Yeah, somewhat better. So I have on the left side the before, and on the right side I have the after. And we're going a little bit through the principles. So essentially, what I've done, which I intend then to incorporate in the library, is I'm using the large files on the left side, and I did a split of the same file into multiple segments on the other side. This is something that is relatively easy to do, given the space on disk. And it allows me to treat each segment separately in parallel instead of the large file. And I didn't have time to incorporate that in the library, but it's on my to-do list, so you don't have to. I want to read in parallel and not have you to split stuff. I have a few cleaning transducers here. I'm trimming the line, I'm removing the blank lines, and I'm splitting with tabs, so I have each single words in a vector when I'm done. And from there, I can do all sort of interesting questions. So let's start with those questions while we are talking. So I have down here, for example, what are the most played artists? And we'll get that started because it's taking less than a minute, but it's taking some time. And you can see I'll bring it up somewhere here. You can see when we are going in parallel or not, it will be displayed on that thing. At the moment, you see a little bit of garbage collector threads, so that's why it looks like it's going in parallel, but it's not. And so there are multiple cores working, but they're working because of the garbage collection going on. So while that is running, I'm just showing you quickly the processing up here. Just to show you the relevant bits, buffered reader is what I'm using with line sec in order not to load the entire file in memory at once. And while I'm scanning through that file, I can apply my transducer here. And when I'm done, I remember to close the buffer reader. And there's a little bit of trickiness, because if I can go editable, so the collection supports transient, I'm switching to transients if I can, which will be most of the time, except one case. So that's why it looks a little bit funny. And it came back in 38 seconds, and Radiohead, that time, 2008, 2009, when the data set was sampled, was the most listened band. What else we can see? We can go down. Top artists in a specific country. Let's make this run. I have an example for Poland, but you can tell me a different country, we'll have a look. And while that is running, let's have a look at what it's doing, but it's more or less something similar. I have an additional filter transducer that I need to add to my transducer chain. I'm calling my process function up there. And then when I'm done, you see that I have to exit the transducer pipeline, entering into, 5 minutes, entering into frequencies and sort stuff and take 5. So this is not happening inside the transducer chain, which is a little bit of a shame. And came back in 27 seconds and so on. So let's start to look into the other side, because I don't have a lot of time remaining. And Where is it? So we have the top artists. I'm using, again, the process function, but the process function now is using the parallel library. And there is a process folder function that is taking all the files in a folder and is giving you back to your transducer chain each line that is found in every file in that folder. So it's very similar, but it's on multiple files. And we can try a few of the examples, but you can already see where I'm going. We are going from, was 27 or 24 before, and we are going down to something like, and this is the one that is not really performing very well because it's got the frequencies and group, the sort by outside. And we are going down to 15, so not very nice, but we can do better, right? Let's see for the artist in Poland if we can do better there. So this is definitely going much faster. And it's coming back in 5 seconds compared to, I don't remember what it was. Oh, it's here. So 37. This is quite a substantial time gain. And we have another query here. How many songs played for a specific band? We can run that and so on, but I want to show you the conclusion of this. I mean, you understand where I'm going with this. I'm partially substituting functions in the standard library with parallel version of them. And I'm making sure that all the complexity that you need to handle, there is mutable state, there are mutable data structure behind this, concurrent data structures. It's all hidden, so you don't need to think about it. But at the end of the day, I'm using fold and fork join with the reducer framework. I'm just making sure that they are consistently returning results the way they should. Let's go back to the presentation. Can close this. So, gotcha. So I think there is definitely a hope in the way you can hide away the complexity of some of those parallel computations. But at the same time, going parallel is semantically different. And you cannot always go parallel, especially with small collections or small computation. So in that case, there's no advantage in going parallel. And that is the same as we have today with lower level parallel APIs. I can drop in just a few of them. I'd like to do more of them. And as I said, not suitable for trivial computations. Nesting is something that should be avoided. I tried a few times to can I freely compose these parallel functions nested in between together? At the moment, you can't. I'm not sure if it's possible because they are going just to, it's going to exponentially explode the number of threads that needs to run, or what are the number of segments that needs to run in parallel. So I'd like to prevent that. So the library should think about that kind of complexity and find a solution. And I'm not sure what at the moment. And I didn't show you a few other features. There's a way to go mutable as an option, and that speeds up way more because I'm not converting back into immutable data structures. And always use a profiler because it's difficult to predict the conditions and the environment in which you will run this. For the future, I'd like to cover more functions, of course, and use them more. And I'd like to see a seamless integration. So if I recognize that the number of core you have available, the amount of data, or the processing you're doing is not enough, I want to switch to sequential and not giving you the slower parallel computation that will happen in that case. There are a few hints to understand if that is happening or not. Still researching on that. And reading input in parallel without having to split into files. So I'm doing that on arrays. I can read them in chunks in parallel. That depends also on the kind of disk you have. Solid state drive is much better, of course. I'd like to do the same on textual file by new lines. And it's possible. I have a couple of ideas on how to do it. More lifting to files. So you saw that frequencies was able to accept transducers and keep everything in a transducer pipeline. But there are others like sort and distinct that I didn't get around to do. I'd like to lift them up so I never exit the transducer loop or pipeline. And maybe, is it possible to go GPU? That would be nice. And see how to do that and how. Closure script, another interesting bit. Concurrency is completely different in the browser, so I'm not sure exactly what I can do there. But I think there are primitives to go parallel. I still need to investigate. A few resources. The parallel library is available on my GitHub account, reborg/parallel on GitHub, and a few papers that might find useful to understand the concepts that are behind fork join and work stealing. The Closure Applied book contains a nice chapter on pipelines and chorusing. And my book, chapter 7 on transducers and reducers, has got a few of the background behind making those things parallel. And that's it. Thank you.
Excellent. Thank you very much, Renzo. Maybe squeeze in one quick talk. I think these two are quick with their hands.
Is there a reason you didn't opt to include something like a parallel do-seek?
No, simply is part of the more functions in the future.
No technical reason you didn't then?
No. I think it's the same way I have a do-to, I should be able to have a do-seek. So all good suggestions, and feel free to pull request that.
Yeah, can you briefly tell how does parallel slurp?
That's the thing that is reading the file as byte input stream. And there are primitives on the byte input stream class that you can use to skip bytes ahead. And so I'm splitting the length of the byte array into like some number of chunks. And each one of the segments, the parallel segments, is skipping ahead of some given amount of bytes to go to a place where nobody else is working at, and slurping the little bit, and then I'm combining everything back into an array. And if you're asking me a string, I'll give you back a string.
So it only works on byte input stream subclasses, right? Not regular input stream, for example.
No. It needs to be a file. Yeah, that's at the moment. Is that the only thing I can support?
Very good.
How do you do parallel sorting?
Parallel sorting. Ooh, all right. I need to remember how I do it.
Offline if you want.
Yeah, I might need to, because I did a long ago, and I don't remember how I did it.
Okay, well that's something. Yeah, so we're in the break. That's a good opportunity to do that as well. So again, thank you for an amazing talk. Thank you very much, Renzo. Thank you.